So for this lesson, we're going to begin our next unit, and in the MCR3U course, this is our final unit. We're going to be taking a look at discrete functions, and these are quite different than anything else that we've looked at so far. Everything we've looked at up until this point would be in the category of continuous functions. So to start that, we're going to take a look at this first lesson dealing with patterns and sequences. And in particular, we're interested in sequences. Patterns are of interest to us because we're going to describe those patterns using sequences. But the sequence is the beginning of this unit and the focus of this first lesson. So I'm giving you to start a very simple sequence, 1, 3, 5, 7, and you can probably from there anticipate that then it's going to go on to 9, 11, 13. Essentially, it's all of the odd positive numbers that form this sequence. So a sequence is an ordered list. Okay, it can be numbers, it can be variables, it can be a combination of the two, and you'll see examples of that as we move forward. We designate or denote each of the terms in the sequence by its term number, where n is a natural number. The natural numbers are the counting numbers. So those are the numbers 1, 2, 3, 4, etc., which in itself you can see is actually a sequence. So that would mean this is term number 1, this is term 2, this is term 3, this is term 4. There may be times when we actually refer to both zero and negative numbers for this, but not to start. So if you've seen something like that before, we will talk about that going forward. But for now, the first term in your sequence is going to be T1, term 1. Now, you can also have a couple of definitions for sequences. You can have a finite sequence, but you can also have an infinite sequence. And they are really just relying on the definition of those two words. A finite sequence means there's a limited number of terms, 1, 3, 5, 7, 9. There are 5 terms in this sequence, and that is it. An infinite sequence carries on. Usually it is denoted by these 3 dots, which is also known as an ellipsis, which just says this is going to continue following whatever pattern has been established up until this point. So in this case, 1 to 3 to 5 to 7, you can think of this as odd numbers, or another way you might think of this more mathematically is that I'm adding 2 to each number as I go. And this second way of looking at it is something that we're going to explore in more detail. Okay, so these terms, term 1, term 2, term 3, they are discrete. And so that means that the number of terms in the sequence is going to be discrete. There's either going to be 1 term or 2 terms or 5 terms or 10 terms. We are never going to have 5.5 terms in our sequence. And because of that, when we decide to try to graph these things, to represent them graphically, it's going to look a little different. This is where we get into the idea of discrete versus continuous. Because there are no values in between. So for example, let's take a look here. Here is my sequence, 2, 4, 6, 8. Now, 2 would be the first term, so 2 would be T1. So the n value that goes with 2 is 1. The 4 would be T2, so the n value that goes with 4 is 2, then the third term, then the fourth term. But if I represent this in this way, I can actually think of these like my x and y axes. So I could, for example, 1, 2, 3, 4, and then vertically I have to go up to 8, so I think that should be my scale. 1, 2, 3, 4, 5, 6, 7, 8. And now I plot my points. When n is equal to 1, my term is actually 2. And when n is equal to 2, my term is 4. And when n is 3, the term is 6. And when n is 4, the term is 8. And the temptation at this point could very well be, well, you might want to draw a nice straight line there, because that certainly seems to be what we've got. But we only have values when the n value is 1. There is no term 1.5. It doesn't make any sense. And so that's what I mean about this being discrete versus continuous. If this was continuous, we might end up with a straight line with arrows on the end, and it stretches in both directions, and it's all of these values in between. But that's not the case here. In this case, there are literally just these 4 points, and that's it. Is it still technically a function? Yes, it passes the vertical line test, so this is a function, but it is a discrete function. Okay, now patterns. What is the relationship between patterns and sequences? If we can find a pattern, then we can represent what's known as the general term using some sort of algebraic notation. So in this case, we've got our first term is 3, which means t1 is 3. Our second term is 6, t2 is 6. Our third term is 9, t3 is 9. And I've also included the fourth term, so t4 is equal to 12. From this, can you anticipate what the fifth term would be? Because once you can anticipate what the next term could be or would be, now you're starting to see the pattern. And so hopefully you realize that the next term here is 15. And the pattern that you might see, first of all, you might notice that we're adding 3 every time. Okay, so that's a good start. The idea of plus 3 has something to do with this. So finding the pattern, okay, we've got the pattern. And now can I write some formula or some algebraic expression that can let me know what any value Tn is? And when you write this, you generally want your algebraic expression. So we want an expression in terms of n. For this to be useful, we want our algebraic expression to be in terms of n. So how does the number 3 relate to n equal 1? How does the number 6 relate to n equal 2? How does the number 9 relate to n equal 3? So even though we first talked about the pattern here being adding 3, if we want to write our expression in terms of n, we actually have to look at it in a slightly different way. So instead of thinking of it as adding 3 and adding 3, how about we look at it as I take this number and do what to it? Well, I multiplied it by 3. I take this number and do what to it? I multiplied it by 3. Now this one is a particularly simple example, but I want to start with something simple. So I'm taking the n value and multiplying it by 3. So my general term here is actually 3n. Now I'm going to talk to you a little bit more as we go forward, maybe not just in this lesson, but as we go through this unit, of some tips and tricks that you can use to come up with these patterns. One thing that I'll mention here would be if we take a look at these, if we take a look at this as a table of values, there's my n value, and here is my Tn. And so when n is equal to 1, Tn is equal to 3. 2 gives me 6. 3 gives me 9. It turns out that first and second differences are actually quite useful. So in this case, my first difference, 6 minus 3 is 3. 9 minus 6 is 3. And this first difference, which we normally label as delta y, although in this case it's delta t, but this delta y, this quite often will have something to do with slope. So first differences have something to do with slope, and now you can see that this makes a little bit more sense in the context of slope. So just keep that in mind going forward. I also notice something in the background here, which is going to, so that's something we just talked about. Each value is 3 times the term number, so we end up with Tn equals 3n. That's what I came up with there. Okay, now how about these next ones? So let's take a look. There's T1, there's T2, there's T3. So let's put a couple of pieces together. First of all, and probably the first thing you might notice, is that in each of these cases I'm adding 5. Okay, now I mentioned to you before, well, that turns out to not be the actual algebraic expression. I'm sure that you can see that the next term here is going to be 25. That's going to be T4. So now let's do something that I just showed you. For n and Tn, when n is equal to 1, I've got 10. 2, I have 15. 3, I have 20. 4, I have 25. Let's take a look at those first differences. 5, 20 minus 15 is 5. 25 minus 20 is 5. These are the same, which means this is a linear. Okay, so there's the first part. And our slope is equal to 5. And so that gives you the hint that Tn has something to do with multiplying 5 times n. But does that go far enough? What is 5 times 1? 5 times 1 is just 5. What is 5 times 2? It's 10. What is 5 times 3? It's 15. It's not enough. And so it turns out we also needed that plus 5 in this case. Now, some of this comes from experience, and some of it, well, you're putting together the pieces, maybe a little bit of trial and error. I'll try to come up with a more kind of a rigorous set of rules if I can for doing this, but I find that there's not a single application of rules. There are some good things to do, and I'll try to demonstrate those to you now. But if I come up with something better, I'll definitely let you know. So how about this one? Here's my first term, second term. I don't want to write all of that out every time, so how about I just go ahead and go straight to my n and Tn. And in this case, I end up with n equal 1 is 1, and n equal 2 gives me 4, and n equal 3 gives me 9, and n equal 4 gives me 16. And you can probably see that the next value to come in here is 25, and that's when n is equal to 5 gives me 25. Now again, I picked this one to be particularly straightforward. Let's take a look at our first differences. There's 3, and then 5, and then 7, and then 9. So those are not the same for delta y. What about our second differences? 2, 2, and 2. So this tells us, because they're the same, this tells us that it's some sort of quadratic relationship. And so that means that my Tn is somehow related to something to do with n squared. And in this case, it's actually only to do with n squared. There's no further adjustment required for that. So this one's pretty simple. It can actually get quite a bit more complicated, because you could have a Tn in the form of a quadratic equation, an squared plus bn plus c. This one we can get, well, we get that from the fact that it's quadratic. So it's pretty simple to recognize. It's pretty simple to recognize this part. And it's fairly simple if you've just got a c. But things get pretty dodgy pretty difficult to determine your A's and B's. It can be done, don't get me wrong, but I think I'll wait until we get to an example more like that. Some people have a pretty good vision for these things and they can really just see them, but of course this is a math course. We want to be relying on more than just plain intuition. So again, as we move forward, we're going to see examples that are a little bit more complex, and we'll deal with those when they arrive. Now in this case, to give you a better feel for it, let's take a look at some examples that are already formed. So here I'm asking for the first 3 terms in each of these sequences. So the long way of doing this is actually to do a substitution. So what we're going to do is we are going to set n equal 1, which means t1 is equal to 2 times 1 plus 1. 2 times 1 is 2 plus 1 is 3. I'm not going to keep writing this part, so now I'm just going to say t2 is 2 times, wherever I had an n, now I replace it with 2 plus 1. You'll notice this is a little bit like function notation, the idea that whatever I set this to be, I then replace that variable with that value. And so this one ends up being 5, and t3, 2 times 3 is 6 plus 1 is 7. So there are my first 3 terms in the sequence. How about this one? T1 is equal to 1 squared plus 4. 1 squared is just 1 plus 4 is 5. T2 is equal to 2 squared plus 4. So 2 squared is 4 plus 4 is equal to 8. And T3, 3 squared is 9 plus 4 is equal to 13. Now if I showed you this sequence 5, 8, 13, you might have a hard time of knowing what to do with that to start. But if we wrote it out, n and tn, and 1, 2, 3, 5, 8, 13, and then we went ahead and did our differences. 8 minus 5 is 3. 13 minus 8 is 5. Actually, well, we don't actually have enough terms here. Of course, we only did 3. But if we had done more, if we had done 4, 4 squared, 16 plus 4 is 18. 18 minus 13, what did I miss there? I did something wrong. No, 16 plus 4 is not 18. 16 plus 4 is 20. 20 minus 13 is 7. 7 minus 5 is 2. Quadratic comes from there. And so then working backwards, you'd now say, well, Tn is some value times n squared. Technically, you would say plus bn plus c. But then when you take a look at once I square these values, then you figure out this other extra piece, this common difference of 4, and it kind of falls out from there. Okay, so some practice here. Like I say, I'm going to work on a more rigorous approach, especially for those quadratic ones. But some practice here and a little bit of trial and error. Give that a try and see if you start to get a feel for things.